Okay, good morning, everyone. Sorry we could not hold class live today, so I'm pre-recording this lecture, but it should be as effective as if we were doing it live together. We'll do the coding activities as well, and I'd like you to follow as best you can and pause whenever there's an activity, do the activity, and then resume. Okay. So last time we left off, we were talking about systems of ordinary differential equations. We looked at an epidemic model and how compartment models can help you develop systems of ordinary differential equations. And that was quite effective and very useful. We saw how to solve those with ODE int, and it was pretty straightforward. Okay. Another type of systems of ODEs that you're going to encounter as chemical engineers come from kinetics with reaction mechanisms, and those are almost identical to compartment models where you have multiple reactants described here as A, B, and C, and they transform. A reacts at a given reaction rate K1 to converts into B, and then B converts into B plus C, and then B plus C goes back to A plus C. So you have all of those rates of reactions and all of those rates of change that work together, and then you can show that you end up with a system of equations like this. You will learn how to derive those equations. These are very similar to compartment models, and you understand how to translate a kinetic system, a reaction system like this, into the governing equations for the concentration of these different reactants. Another situation where ODEs result in systems of when you get systems of ODEs is when you are dealing with high order ODEs. So far we looked at first order ordinary differential equations, so those have a first time derivative in them. There's another situation where you have second order or third order ODEs and so on. Turns out and for initial value problems that those ODEs can be converted into first order ODEs. Now why do we do the conversion? Because dealing with first order initial value problems is extremely easy. We know the theory and we know all about time integration methods for first order ODEs. They're easier to integrate and solve, and therefore it makes sense if we can recast everything as a first order initial value problem. A classic example for this would be Newton's law. When applying Newton's law, so a force balance on an object that's thrown to the earth. At time t0, you release an object, a ball for example, and it starts falling to the earth. It has position x as a function of time, and velocity, speed, v as a function of time. Now, at low Reynolds number, the drag force is proportional to the velocity, and the governing equation looks like this. So you have acceleration is equal to minus alpha times the velocity, that's the drag force, and then there's the gravitational force. So summation of forces is proportional to the acceleration. Initial conditions are, you need two initial conditions here because you have a second order derivative. So you need x at 0 and dx by dt at 0. So we assume the initial position is 0. And the initial speed, so you're not throwing it at a speed, the initial speed of the object, just releasing it, is equal to 0. So now take a moment and think about how we might be able to solve this problem. Think about what we did last time with first order ODEs, our solution strategy, and think about what we might be able to do in this case. I would press pause, think about it, and then come back. Okay, to give you the answer, the strategy, the simplest strategy would be to convert this high order ODE into a system of ODEs. There's a simple way to do that. You simply take the first derivative or the lowest derivative in the system, give it a symbol. So in this case, we're going to call dx by dt, we're going to call that v. And then you say that d2x by dt squared is equal d by dt of dx by dt, which is v. So that makes it a first derivative. So you get dv by dt equal g minus alpha v. And that's how you convert a high order, second order ODE into a system of two ODEs. If you had a third order, you're going to get three equations over here, obviously. And the initial conditions translate as you would. So x equals 0, that still applies for this ODE. And v at 0 equals 0 now applies to this second ODE. Here's another example where also looking at an object, but at high Reynolds number, like a skydiver falling in the atmosphere, the drag force is proportional to the square of the velocity. So you have a dx by dt squared over here. And same thing you do, you call dx by dt equal to v, it's just a variable name, and then you get another equation for dv by dt. This is by far the simplest strategy to deal with high order initial value problems. Now you could say, and as we will learn in the next section, we can discretize this or convert it into using finite differences, but it doesn't work quite well for these initial value problems. This solution strategy is much more elegant because you're just dealing with the first derivative. You don't have what's called the startup problem, issues like that. This is a good strategy to deal with initial value high order derivatives. All right. The next section we're going to talk about is we're going to get under the hood of ODE. And a challenge in this class has been always to answer the question, how far do we go into the program? Should we just teach you, expose you to the methods like ODE int or fsolve that are used to solve these complex equations, or should we go under the hood and see all the details of what goes on? I think we need both. You need to be exposed enough to the programming, to the complexity of the programming, to see what it takes to make this happen. But you need to understand the theory. That's numerical methods. You need to understand the theory, definitely. Sometimes, in most of the times, I have given you the algorithms, but then it is up to you to use those algorithms to put things together to solve the problem. So overall, I think the strategy we've adopted in this course is somewhat complementary and comprehensive in the sense of for you to identify what tools are needed to solve a certain problem and how to use those tools. And then you can dig in deeper as much as you like. Now, under the hood of ODE int, we're going to look at what ODE int is doing behind the scenes to solve these differential equations. We're going to start with the simplest time integration methodology, and that's called explicit time integration. And there's a reason for why we call it explicit, and you'll see that in a moment. All right, so suppose we are solving the ODE as we've written it, dphi by dt equal to some right-hand side of t and phi. So the right-hand side could be anything, could be a function of time, could be a function of the dependent variable, be a function of both, okay? It could be linear, non-linear, whatever you want, we just call it right-hand side, r of t and phi. And given the initial condition, phi at t equals 0 equals some initial value, and you want to solve this ODE from t0 to tn, could be from 0 to 10 seconds or 1,000 seconds, doesn't matter. So to depict this system, right now we have a value at phi0. That's the only thing that we are given. And our purpose is to find the values of phi in between t0 and tn. And the only thing we know about phi is its slope. And we know that that slope depends on the value of phi itself, because the right-hand side is going to depend on phi and time as well. But we are starting over here with phi0, and our goal is to find this curve. In other words, to reduce t0 and develop a recipe so that we can recursively find the individual values of phi or the straight curve. Okay? Now, in practice, we cannot continuously find this curve. We can find it only at discrete values. And we saw this early on in the semester when we were doing the heat transfer problem. This takes us further deeper into why we did this. So the first step is to subdivide the timeline into a discrete set of points, because we cannot solve this continuously. This is not analytical method. We have to do this discretely. So we're going to choose to divide the timeline, the time domain, say at a fixed interval. You know, let's call that interval delta t or h. I'm going to use those interchangeably, so don't confuse the two. Okay, and our goal then would be to find the value of phi at all of those time intervals. Now, for simplicity, we call the first time at t0, the second one t1, t2, and so on all the way to tn. Okay, this could be equally spaced or not. For simplicity, we're just going to do it equally spaced. Okay, and then our goal would be to find phi1, phi2, and all the way to the end. All right, so what we know is phi0. What we do not know are phi1, phi2, and all the way to the phi end, right? So now we want to develop a recipe to find those values. Now, what do we know? we know the governing equation. We know that d phi by dt is equal to some right-hand side. So what if we say, okay, d phi by dt at t0, we're going to take the governing equation and say d phi by dt at t0 equals, identically equal to r of t0 and phi0. Is this not correct? That is correct, because the governing equation is valid. We assume the governing equation is valid over this entire timeline, and therefore it's going to be valid at every interval, at every point in this interval. And therefore, this is a completely legitimate statement. Now, we're going to bring in something we learned about finite differences when we approximated derivatives. We're going to go ahead and approximate this derivative using a forward difference formula in this case. So the forward difference formula tells us that d phi by dt at t0 is equal to phi1, the next value in the domain, minus phi0 over the distance between these 2 points, which is delta t. Okay? We do not know phi1. Okay? Our goal is to find phi1, but we're going to use this formula now to find phi1. Now this commits an error of order h, and that's why I kept the equal sign, the exact equal sign. I didn't put approximate because I kept the order h. And that is going to be equal, to r at t0 and phi0. Okay? So now I use an approximation by dropping the order h, so I put the approximate sign, so I get a formula for the governing equation at t0. That formula says phi1 minus phi0 over h, or delta t, is approximately equal to the right-hand side at t0 phi0. Now, in this formula, what is known and what's unknown? Phi0 is known, that's given to us, right? And right-hand side, we know the form of the right-hand side, correct? Because that's the governing equation. It could be d phi by dt is equal 5 phi squared times t, right? So we know the structure, the formula for the right-hand side. And at t0 and phi0, those are known values, right? So we can directly evaluate this right-hand side. So this entire thing is known on the right-hand side. And the only unknown in this equation is phi1. H is known, phi0 is known, right-hand side is known. Then the only unknown is phi1. So we can simply solve for phi1 by extracting it, and you get phi1 is equal to phi0 plus delta t right-hand side. What this formula is really saying is that the next value is equal to the previous value plus the interval, okay, times the rate of change at the previous value. So really this r, in other words, is the equivalent of the rate of change of the curve at that point. All right, so great. Now we get phi1 equal phi0 plus h plus delta t times right-hand side at t0 phi0. And now we update, we are at our time, t1 is equal to t0 plus delta t. All right, so now go ahead and take a moment and solve for phi2 in terms of phi1 and t1, phi3 in terms of phi2, and so on, and all the way to the end for phi-n in terms of phi-n minus 1 and t-n minus 1. Okay, so simply just apply this formula again. Now you are at phi1, you know phi1, you know t1, obviously. Now apply the same equation, the same formula, the governing equation, apply it at this point, use forward difference to predict phi2, and so on. All right, so I'm assuming you've taken a moment to do this. And so very simply, phi2 is a replica of this previous formula. It's phi1 plus delta t times right-hand side evaluated at t1 and phi1. And phi3 is phi2 plus delta t times right-hand side evaluated at t2 and phi2, and so on. And phi1, sorry. Phi3 is at phi2, right? And all the way to an arbitrary point in this domain, arbitrary point n, phi-n plus 1. If you know phi-n, then you can predict the next value. It's like you are moving in time. That's the beauty of initial value problems. You know your current state and you're predicting your next state. Okay, so phi-n plus 1 is simply the known value phi-n plus delta t times the right-hand side evaluated at the known value. And that formula is called the forward Euler method. And this is one of the simplest time integration routines that is very widely used to solve ordinary differential equations. It can be applied to a single equation or to a system of equations. Okay? So the algorithm is pretty simple, and I'll share with you the code. We'll do the lobster example and a couple other examples. Okay? But given phi-n, t-n, t-n, and delta t, and the right-hand side, assuming that you know all of those, or in other words, given phi0 and t0, right? You set tn plus 1 as equal to Tn plus delta t, and then calculate phi n plus 1 equal phi n plus delta t times the right hand side, evaluate it at n, at all the previous value, then update your Tn, update your phi n, and repeat. Okay, repeat. I'm going to show you a little clip over here. I'm not sure that it's going to record.
The problem
Let me try.
is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not your math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you it is.
Euler's method,
Euler's method.
yes.
But that's ancient.
But it works. It works numerically.
I love this scene. Gives me goosebumps every time I listen to it or see it. Beautiful movie, a great movie, very inspiring.
That's it.
Let's type it up.
All right, beautiful, inspiring story. Now the specifics of what they used, what Dorothy used in that was not necessarily the forward Euler method. It was something different, a little bit different, but still, you know, I'd like you to think that this is the forward Euler method, but she used something very basic, very elementary to calculate, to predict the orbit for Glenn to launch him into space, and that set us at the forefront, really what dictated the second half of the century for the United States leading the world. This is one critical contributing moment. So don't underestimate the methods that you're using here and the simplicity and beauty of these simple methods and how you can use them. Be inspired. Okay, watch this movie. I watch it once a year just to keep me alive. All right. So here's an example. Take d phi by dt equal minus t squared phi to the power 4 with initial condition phi 0 equal to 1. This is the forward Euler formula, phi n plus 1 equal phi n plus delta t times right hand side evaluated and Tn and phi n. Now you're going to do this next exercise by hand. I'm going to ask you to use a time step size of 0.5 seconds. So in other words, you're starting t0 equals 0, t1 is 0.5, t2 is 1, t3 1.5, and so on and so forth. All right. So now first step is I want you to express the right hand side in terms of t and phi as specified in the governing equation, right? So to do this, very simply, you get phi n plus 1 is phi n plus delta t, which is 0.5, times the right-hand side at tn and phi n, so times minus tn squared times phi n to the fourth. So if you know everything at n, you can predict the state at n plus 1. All right. So next, now I want you to calculate phi 1 numerically. Pause the video, go ahead, do the calculation using this formula, okay? If you've done this correctly, phi 1 is phi 0 minus h t0 squared phi 0 squared. You plug in the numbers, you get phi 1 equal to 1. Go ahead and do phi 2. Pause the video, take a moment, do the calculation, come up with a number. Right? In this case, phi 2 is, again, phi 1 plus delta t times right-hand side at 1. Everything at 1. You plug in the values, you get 0.875, and so on and so forth. Phi 3 is the same thing. And phi 4 is the same thing over and over again. So you just repeat this all the way until you get to the last point. And that's how you integrate numerically the first order ordinary differential equation. All right. To turn this into a Python code, I'm not going to ask you to do it. I'm just going to give you the code. We're going to use it in one of the Jupyter notebooks, but you can always rely on ODE. But there's a reason for why I want to show you this, is to motivate you for what we're going to call implicit methods later. So now I want you to take a moment and think about what would you need to do to write a pseudocode. What would you need to do in order to implement the forward Euler method in a Python code? So what arguments does the routine require? Do not worry about passing additional arguments to the right-hand side right now. Just assume that the right-hand side is only a function of t and phi, and that you define all other coefficients, etc., outside, or hard code them. And what should the routine return to you? So pause the video, take a moment, and think about this. Okay, if it were me, I would first declare my method, call it forward Euler, and the forward Euler method needs at a minimum the following. It needs a right-hand side value, or right-hand side function, so that it calls it. It needs an initial condition, and it needs an array for time, just like ODE int, okay? Now you can substitute this array for time with a time step size, delta t, and a t end, so that you know, or t0 and t end, so that you know where you're starting from and where you're ending up, okay? First, I would create an array for the solution, okay? And then initialize the first point of the array as f0 equal the initial condition, and then loop over all time steps. And then for each time step, do fn plus 1 is equal to fn plus delta t right hand side at fn and tn, and then return f in array, okay, at those different times. Okay, I would also probably return the time, well, because we declared the time as a linear space over here, time array, then we don't need to return the time array. But if you were using dt over here, you want to return a time array so that you can plot f versus time. So this is the algorithm given here to you, and there's another one, another form where I use the fixed time step size, okay, and I provide the routine with the end time, and notice here I return the array for time and f as well, okay. So now go back to your lobster example with the gaps in the middle. So first we used ODE int, right hand side radiation, right hand side convection. Now we're going to do it. There's a section called using our own integrator. I just want to play around with this a little bit to show you how we can call the forward Euler method. The forward Euler method should be already pre-programmed in that notebook, so we can just use it and call it. All right, I'll see you in a second. Okay, so now we are back to our lobster with gaps example. If you don't remember the problem, go ahead and remind yourself what we were doing. We had defined right-hand side convection, right-hand side radiation. We used ODE int, etc. And then we did another example by passing parameters to the right-hand side. We're not going to do this with our own forward Euler integrator. So we're not going to be using these right-hand side functions. Instead, we will be using these two defined previously over here. Okay? But if you keep scrolling down in the notebook, you will see a section called using our own integrator. And in this one, I'm using one version of the forward Euler method, where it takes the right-hand side initial condition and a time array for time. And then I go ahead and do the coding. Feel free to read through the code to understand what I'm doing. First, I define the number of steps, which is the length of time points in the time array, and because I need this to count to loop over to loop over time. And we're going to also assume that the time step is constant, and simply taking the difference between two times in the time array is going to give us the time step size. I initialize my solution variable as a NumPy array of zeros of the same size as n steps, and I start my initial point as f0, and then I do my loop over all the time steps, and I do fn plus 1 is fn plus delta t times right-hand side. Couldn't be any easier. So go ahead and execute this cell. And now let's run the simulation for cooking the lobster. T end is 20 minutes, but time is in seconds, so I'm going to do 60 times 20 to give me things in seconds. I'm going to declare my time step size to be 10 seconds, okay? And based on that, I'm going to create the n steps and a linear space so that I get my desired delta t. Okay, you could have done that differently. You could have just declared len space with 50 points or 100 points or 1,000 points. Doesn't matter. Initial condition is T0 equal 311. And now the solution for the temperature of the lobster using convection, I just call forward Euler. I give it right-hand side convection. Remember, this is the first one over here, right-hand side convection, phi and t. Okay, so t and time, in other words, and that's what this is going to call every time. So you see, that's why we needed to declare the right-hand side in a certain way, because inside the routine, inside the forward Euler method, or whatever ODE it was using, it is always calling this right-hand side, and it needs to know how to call it. It needs to know the ordering of the variables. Is it t and then is it dependent independent variable or independent dependent variable? Is it arguments before those other dependent independent variables? That's why we need to make this unambiguous. That's why we followed a convention, that the right-hand side is always declared as right-hand side dependent variable, comma, independent variable. And then simply you call it on RHS convection, RHS radiation. You execute, and then you plot, and this is what we get. Now you can change the time step size. You could go to 5 seconds. It's going to probably give you a little bit more accurate results. If you go to very high time steps, you might get into trouble. Okay, we're going to see the trouble a little bit later, but you see what's going on here. You start getting this kind of low resolution solution, and eventually, if you go very high time step size, you're going to get into trouble. Actually, this is what you see, and we're going to talk about this next, okay, and why the forward Euler method is a little bit problematic. All right, so run this again. This is your solution. Okay. All right, the next example that I have is a system of equations, and that's the SIR model, the SIR model for epidemics. And I want to show you that you can apply the forward Euler method to a system of equations as well. And you're going to do this example by hand, actually. I want you to try to apply the forward Euler method to this system. Recall that the FE method is given by the formula phi n plus 1 is phi n plus delta t times right-hand side. Assume initial conditions S0, I0, and R0 for all of these equations. So just do the things symbolically. Okay? Take a moment. All right. So simply, this is telling us with the forward Euler method that Sn plus 1 is Sn minus delta t beta over n In times Sn. In plus 1 is In plus etc. And Rn plus 1 is Rn plus delta t gamma In. No, remember that you know everything at state n, at time n, and you're predicting things at time n plus 1. Okay? Now, take these formulas and consider the following conditions. Initial condition for S0, Si, and R are 9, 1, and 0. So initially you have 9 susceptibles, 1 infected, and 0 recovered. Total population N equal 10, beta equal 1, gamma is 0.05, and delta T equal 2 days, and then just take a single time step. Now remember, in this case, the units are in days, so you don't have to convert delta T to seconds, okay? So if you go ahead and do the calculation, you just simply substitute the numbers. It's an exercise that you should do by hand because you might end up doing that in one of the exams. So just do the homework. So just do this by hand. Make sure you get these numbers. And if I am mistaken in any of those, please let me know so that I can correct it for next year. All right. So when we solved the lobster problem, we ran into a little trouble when I made the time step 50, or very large time step size. We started seeing these wiggles, like these oscillations, okay? And there's a reason for that, and I want to motivate you to do this, and I want you to go ahead and from Canvas download Motivation for Implicit Methods with Gaps. If you can't find this in the modules section of the course, it should be under Files, Jupyter Notebooks, okay? So go ahead and download this notebook, please, and we are gonna work through this together. Okay, so I'm gonna assume that you're downloading it. You pause, download it. Okay, so what we're gonna work with to motivate you to move beyond forward Euler is we wanna consider this ODE, d phi by dt equal minus 1000 phi with an initial condition of phi 0 equal to 1. Okay, the exact solution looks like this. There's a very sharp decrease and then it flattens out. Okay, very strong exponential decay. And my goal is for you to try to use the forward Euler method, just like we just did in class. Use this notebook, choose a bunch of different time step sizes and see if you can solve this problem. So if you take this notebook, you should see forward Euler method, the exact solution, and some hooks in there for you to try to solve this equation. Try it at different time step sizes. Okay, start with time step size maybe 0.003, maybe go up, maybe go down, and let's see what you get. Okay. All right, so if you've done this correctly, what you've probably observed is that for some time step sizes, you're gonna get strange behavior, strange looking solutions that don't make sense. Okay, until you keep decreasing the time step size until it becomes, you capture the trend of the solution. All right, so what I'm going to show here is some of those results. With delta t equal 0.003, this is what my code gave, and you should have seen this. You don't capture anything. Remember, the exact solution went down like this and then went to 0, whereas what we're seeing here is just 0 everywhere and then oscillations at the end, which do not make sense. Then if you decrease your time step size to 0.002, what you get are just random oscillations, okay? And far away from the solution. And then you keep decreasing delta t to 0.001, that's where you get something that is okay, that looks okay. You start at 1, and then you essentially just go to 0, okay? Still not very accurate, but it captures the trend, right? And then as you decrease your time step size, so you put more points on that approximation, then you start capturing the curve better and better, okay? Now, there is a reason for why this is happening. The intuitive explanation is that when things change abruptly, explicit methods need a lot of points within that interval to be able to capture that interval. Otherwise, we say they become unstable, and we'll define stability in a moment. But these are unstable solutions. They don't make sense, they diverge, they give you nonsensical answers, okay? Now, one could argue then, let's use an arbitrary large number of points to solve all of the problems with forward Euler or explicit methods. The challenge is that this sharp transient occurs on a very small interval, and we ended up resolving it with like 5 points. But then we had this huge interval over here, probably required 1,000 points, where very little change was happening. Okay? So one of two things you could do. You could say, when things are changing fast, I need more points, so my time step becomes smaller. But then I can increase it in regions where there's not much change. That's called adaptive time stepping. It's beyond the scope of what we're learning here. And still is not a bulletproof solution, because you still need to anticipate where a sharp transient or where a sharp change is going to happen. The other alternative is to look for implicit methods. Okay, now mathematically, I'm going to give you a basic explanation for why this happens with the forward Euler method. We're going to take this equation, a model equation, d phi by dt is minus a times phi. We're going to assume a is a positive number with an initial condition phi of 0 equal phi 0. Now in our case, a was 1,000, so we had 1 minus 1,000 phi. Now if you apply the forward Euler method, tells you phi n plus 1 is phi n minus delta t times a times phi n, okay? And that means phi n plus 1 is 1 minus ha phi n. Now, in our case, for this particular problem, we know that the solution is decreasing, okay, over time. And therefore, we require that phi n plus 1 in magnitude is always less than phi n. Now, what that means is that 1 minus delta t times a is less than 1. And therefore, that gives you a condition on delta t, or the time step size, that delta t, for this to be true, for phi n plus 1 to be less than phi n, then delta t needs to be less than 2 over a. So in other words, to be stable, our delta t needed to be less than 2 over 1,000 in our case. And in other cases for A, that's a condition of delta t. So there is conditional stability in this case. Now, you can meet this condition and have a stable integrator, but you're going to have to do a lot of points, like in that example we did. Okay? Implicit methods circumvent this stability problem by using information from the future. Ooh, it's like they travel in time, bring information from the future. There's nothing mysterious about this, and we'll know what this means in a second. If you think about the forward Euler method, we said we are evaluating the derivative, the equation, instead of when we started at phi 0, we said, okay, we're going to evaluate the rate of change at phi 0 to predict phi 1. Or we use the rate of change at phi n to predict phi n plus 1. Implicit methods do the opposite. They say, I'm going to use the rate of change at n plus 1 to predict phi n plus 1. Okay, so let's see what happens. In explicit methods, again, we said we're going to use the rate of change at n, and right-hand side, everything is at n. Okay, and then you use a forward difference over here, and this is what you get, phi n plus 1 minus phi n over delta t, everything is at n, so that's how you resolve this. Implicit methods, they use the future. They say we're gonna evaluate phi n plus 1 by looking at the rate of change at n plus 1. So d phi by dt at n plus 1, everything is at n plus 1. Excuse me, now, to discretize this, we need to relate this to something we know from the past. We can't do a forward Euler, because if we do a forward Euler over here, then we get phi n plus 2 minus phi n plus 1, and that brings us back to explicit. So over here, we really need to do a backward difference. So if you do a backward difference, then you get phi n plus 1 minus phi n over delta t. It looks the same as this one, right? But the right-hand side, the rate of change is evaluated at n plus 1. And this is called, the backward Euler method, okay? Look at the similarities. The left-hand side and the left-hand side are similar, but the right-hand sides are not similar. This is using information that is known. This is using information that is unknown. Yet, we don't know what r at n plus 1 at phi n plus 1 is, because we don't know what phi n plus 1 is. And that's why it's called implicit, because you have phi n plus 1 and phi n plus 1 on both sides. Okay? Now, to write it similar to the forward Euler method, you get phi n plus 1 for the backward Euler is equal to phi n plus delta t times right-hand side at phi n plus 1. Okay? Now, the first exercise I want you to try to do is show that this equation, using the same argument that phi n plus 1 needs to be less than phi n in magnitude, in absolute value, show that this method is always stable, is unconditionally stable. Take a moment, try to do the derivation, look through the slides from my PDF, look at the previous slides, okay? But just try to show that phi n plus 1, what are the conditions for phi n plus 1 to be less than phi n? So here's what the formula is for the equation that we dealt with. d phi by dt is equal minus a phi. Hence phi n plus 1 equal phi n minus delta t times a times phi n plus 1. Now what you get, phi n plus 1 is 1 over 1 plus delta t a times phi n. Now phi n plus 1 is less than phi n so long as delta t is a positive number. Okay? And delta t is always a positive number because that's the time domain, right? It's always positive. And therefore, this number is at most 1 and it's always less than 1. In other words, phi n plus 1 is always less than phi n, and this method is always stable. Okay, guarantees stability. It's unconditionally stable. Graphically, forward Euler is using the derivative at the previous time, okay, the rate of change at the previous time, and backward Euler is using the derivative at n plus 1, the rate of change at n plus 1. But there's one caveat over here. If you look at the backward Euler method, okay, this is in general a nonlinear equation. Okay? I want you to take a moment and think about this very carefully. Why is this a nonlinear equation? Phi n plus 1 is phi n plus delta t times right-hand side. The right-hand side could be anything, remember. Right-hand side, tn plus 1 and phi n plus 1. Take a moment and think about this. Okay, now that you've thought about it, this right-hand side could be anything. What if it's cosine phi? Okay, then you would have phi n plus 1 is equal to phi n plus delta t cosine phi n plus 1. You have phi n plus 1, phi n plus 1. You have a cosine. It's a nonlinear equation. In general, you have no control what the right-hand side is. It doesn't have to be linear in phi, it can be nonlinear in phi. And anytime you have an implicit method, you might end up with a nonlinear equation. And in this case, for every time as you are advancing in time, rather than what we did with the forward Euler method where we simply evaluated phi n plus 1 using an algebraic manipulation, over here, for every time step, so you're moving from n to n plus 1, for every time step, you are going to have to solve a nonlinear equation, this nonlinear equation. And the residual function from this nonlinear equation is, we're going to call it a g, okay, rather than r. It's simply, you know, put everything on one side. We're going to move everything to the left-hand side. So it's phi n plus 1 minus phi n minus delta t times right-hand side, okay? Now this is general. This is a very generic form for all backward Euler methods, regardless of the right-hand side. Okay, if the right-hand side is linear, then that's fine. The nonlinear routine that is going to solve for this residual function is just going to find the solution. Or if the right-hand side is nonlinear, it's still going to find the solution. So that's the only difference, and it's a critical difference between a forward Euler and backward Euler method. Okay? An algorithm for the backward Euler is that you're given a current state at n, you know phi n, tn, you know tn, you know your time step size, and you know the formula for the right-hand side. You start with a guess for phi n plus 1. Typically, you say phi n plus 1 is equal to phi n. That's my initial guess. That's my, not my initial guess. Yes, that's my initial guess for the nonlinear solver. You set that tn plus 1 is tn plus delta t. You solve for the residual function g phi n plus 1 equals 0 using Newton's method. So this would be an f solve over here. And then you do the same thing as you would have done with forward Euler. You set tn is tn plus 1, so you move time back and then you repeat, okay? Or you do it in an array, it doesn't matter. But you just have to advance, and every time step you have to solve a nonlinear equation, okay? And here's an example. dc by dt equal minus kc squared. Clearly this right-hand side is nonlinear because the dependent variable c shows up nonlinearly. And the backward Euler method tells us that Cn plus 1 minus Cn over delta t is minus k Cn plus 1 squared. And if you take out that equation, it's nonlinear, and your residual function is k delta t Cn plus 1 squared plus Cn plus 1 minus Cn. Notice I just changed the sign over here in this residual function. It doesn't matter because it's going to be set equal to 0. Numerically, you can use fsolve, or you can do your own routine. You need, with Newton's method, you need the derivative, and then you can estimate, do a few iterations. You are going to be responsible for this because this brings us back to nonlinear solvers. Now, see how everything is tying in together, right? Linear solvers, nonlinear solvers, and ODEs, everything ties in together, and that's why we study things in that order, because this is the culmination of what we've been studying so far. Okay? Do this, you know, example by hand, and then you can move on one step at a time. Okay, it's really, once you write this equation, this is just a nonlinear equation. You get an update, you update Cn plus 1, you use that as your, you know, your new initial value if you want, and then you move on. Okay. Another example are cyclical systems, and this is another example for another time integrator method. So right now we only really talked about forward Euler, backward Euler. They are both first order methods. So because the approximation for the derivative is order delta t. Okay, so all of those methods are first order. Okay, we can develop higher order methods using also finite difference formulas, and you know that becomes beyond the scope of what we're interested in over here. But this is just giving you a flavor of what we want to deal with. Now, another system that you might end up dealing with are cyclical systems where, you know, say you're driving your car and there are humps and you're kind of bouncing up and down, or you go through a Ferris wheel and your position is changing over time. So it's a cyclical system. Looks like, you know, dy by dt is r omega sine omega t, where omega is the frequency, and, you know, whenever you see a sine and cosine, you have some type of cycle. Now, for this equation, dy by dt r omega sine omega t, this is an example of what I get with forward and backward Euler. So the blue line is the exact solution for one of those systems. So I fixed the value for omega and r, and I solved it, and you get something like the blue line. But if you use the forward Euler method, you're going to get the curve in red. And you see there's a phase shift to the right of the curve. If you do the backward Euler method, you have a phase shift to the back. And understandably, because that's the forward Euler method and the backward Euler method, they're going to bias you in one direction or another. It would be cool, though, if for cyclical systems, we know for a fact that forward and backward Euler are not a good idea for cyclical systems, but it would be cool if we can kind of average them together. And this is what the Crank-Nicholson method does. It essentially takes the average between the forward Euler and the backward Euler method. So this is the forward Euler method, this is the backward Euler method. Look, the left-hand side looks the same, but the right-hand sides are different. What this method does, what the Crank-Nicholson does, it adds them up together and divides by 2. So essentially the left-hand side remains unchanged, but the right-hand side you're combining something from the past and something from the future, and you're weighing it in half. This is still a nonlinear equation in general, because although you know R of phi n Tn, you don't know R of phi n plus 1 Tn plus 1, and that's what makes it nonlinear. Okay? And you also define a residual for Crank-Nicholson. It just looks like this. For backward Euler, this didn't exist over here. We didn't have this term. We didn't have the 1 over 2 either, but we didn't have this term. We only have that term. But the Crank-Nicholson just adds something from the past. And visually, forward Euler is biasing, to one side, backward Euler is biasing to the other side. Crank-Nicholson is somewhere in between. Okay? And the algorithm is the same, identical to the backward Euler method, except that your residual function is going to change. Your residual function is going to be this guy. Okay? And as you can see here, if you can see it, the Crank-Nicholson actually fixes the phase shift. It doesn't capture the peak correctly. I can capture the peak better if I do more time steps, but there's no phase shift neither to the left and to the right. And typically it's the frequency that matters in these problems. So if you miss the frequency, the amplitude is important, but the frequency is more important, okay? And again, visually, this is what you would expect for the Crank-Nicholson method. It's kind of somewhere between forward Euler and backward Euler. Okay, and with that, I'm going to finish this lecture. Now we looked under the hood of ODE Integrate. The remaining parts of this chapter are going to be some of the hardest. We're going to look at boundary value problems. Unfortunately, it's going to be hard to do boundary value problems with ODE Int. We can't do it really. So we have to kind of hard code everything. We have to look under the hood for boundary value problems, and especially when they become nonlinear, that's when it becomes really, really nasty. Okay, we will do that next week. Thank you so much for your attention. I apologize that I couldn't be here with you live today, but I hope you pay attention here and do not hesitate to send me any questions that you might have. Thank you so much.